right. Well, nice introduction. Let's go ahead and get started with the meat of today. This is the second episode, as I said, in my kind of stellar aberration series. There's clearly two more, at least. I'm thinking probably three more. I'm trying to bite off little tiny pieces of it. Yes, last week's really was, even though it was relatively long, because I had a lot of background information in there. The meat was pretty short, and today's meat is pretty short as well, but it does run to a number of slides. So let's just go ahead and start. If you open the Google Slide document at the top of the room, you can follow along. You see this is the corpuscular view. We're going to talk about Bradley's explanation of stellar aberration, which I talked about last time, from the then current view of light as being particulate corpuscles of light. Newton thought that, and despite the fact that there was already some pretty good indication that you couldn't of things that you couldn't explain with a particle view, that was really the dominant view through the 1700s until the kind of early 1800s, which will be where we start next week. So just to review a little bit, on slide 2, last week we talked about what Bradley was doing. Bradley was looking for parallax. At this point in the wake of Newton, et cetera, we understood the heliocentric model of the solar system, that the Earth was moving around the sun. We knew kind of how far away the sun was. We knew it was, 50 to 150 million miles away, maybe a little more accurately than that. So we knew that the Earth had to be moving at some 20 to 40 kilometers per second around the sun to make its orbit, the circumference of that orbit, in 1 year. And so we knew that kind of thing. And then the idea was, well, when we look at stars, we should see them at a different place in December than we see them in June, because we're, a couple 100 million miles, say, on the other away from where we are in June. A nearby star should move relative to background stars by just the simple idea of parallax. You move your head back and forth. Nearby things seem to move more than far away things. And so he was looking for parallax as a way to get an idea how far it is to the stars. And he ended up seeing a shift in the star's position, but it wasn't the shift he expected. He expected, as the diagram on that page shows at the left, that when in December, you should see the star kind of shifted over to the right. And then in June, it should be shifted over to the left, et cetera. And as you go around, the star should describe a little circular path. This is for a star that's directly above the ecliptic plane, the plane of orbit of the Earth. Stars in different positions would actually describe slightly different paths, elliptical paths rather than circular paths. If you think about that, you might see why that is. And he saw this kind of thing. The problem was it was 90 degrees out of phase with what he expected. In December, rather than the star shifting over there to the right, as shown in the diagram on the left, it actually shifted kind of out of the page. It shifted in the direction of the Earth's motion, not opposite the position of the Earth, but shifted into the direction of motion of the Earth. And the same thing was true in March. In March, when the Earth was moving to the right, the star was shifted to the right, etc., and so on, all the way around. And that means a kind of a path that's 90 degrees out of phase. That's what he expected for parallax. But it didn't take him long, slide 3, to kind of understand this in terms of this rain of particles coming down on the Earth, particles of light coming down on the Earth. As the Earth moved through that rain, it would appear to be coming more from the direction in which the Earth is moving. Just like if you move through actual rain, you have to tilt your umbrella forward to shield your body, because now to you, the rain appears to be coming down at an angle tilted toward the direction of your motion. And as the diagram shows on the right side of that picture, Yeah, if you had a telescope, that telescope, if the Earth weren't moving, might be looking straight up at the star. But now that the Earth is moving with that speed, that light comes at an angle alpha, and you have to tilt the telescope so that light can go make it down the barrel through the optics into the eyepiece so that you can see it. Now that angle alpha is really small. There's no question about it. Bradley measured an angle that was a tiny fraction of a degree, a tiny fraction of a minute of arc, which is not a tiny fraction, but a pretty small fraction of a minute of arc, which is a 60th of a degree. What he measured was about 20 seconds. He had to tilt the telescope about 20 seconds. And we talked a little bit about the specifics of that last week. I'll just remind you of that on slide 4, where I've reproduced a diagram, at least a part of a diagram that I showed last week with a supplemental thing. So what I'm showing here is the Earth going around the sun, once again, in the winter over there to the left, and in the summer over there to the right, winter, northern hemisphere, summer, northern hemisphere, etc. And he was looking in particular at a star, a really nice star called Gamma Draconis, which goes almost directly overhead in London once a day, every day, all year long. And that's an important thing to appreciate because the star is so far away, it always appears the same direction from Earth. And since the Earth's tilt doesn't change as it goes around the sun, once a day, that star passes overhead in London. I show you a blown up picture of the Earth, kind of see how that works. There's the Earth tilted, as it is in the diagram to the left. And there's the latitude of London. London gets carried around there every once a day. And once a day, that star, quote, goes directly overhead, of course, because London is carried directly underneath it. Now, his telescope was rigged so that it could only change its orientation in the north-south direction. He didn't care to measure deviations in the east-west direction because that would have required him to know very accurately what time it was every day. But if he just looked at the passage overhead, it didn't matter really what time it was. All that mattered was, is the star shifted to the north or south at the time, whatever it is, that it goes overhead. And so that's what he was looking for. And so if you take that bigger picture, keep that bigger picture in mind as you look at the bottom there, you can see that in the winter, when the Earth is moving kind of toward us out of the page, the light from the star will be shifted toward what would be at London the west. It would be shifted out of the page as well. If you look at the upper diagram there, I think you can see that means that the star appears to be a little more to the west. And that actually means that it'll cross over London at a slightly different time. But once again, he wasn't sensitive to that, so he didn't notice that shift. 3 months later in the spring, when the Earth is now moving to the right, the star will be shifted to the right. And once again, if you refer to the big picture, you can kind of see that shifting to the right corresponds to the star appearing to be at a lower position in the sky, a southerly position in the sky. So the star will shift southward in the spring. And then in the summer, it's kind of the same thing as the winter, except it shifts the other way, undetectable. And then in the fall, because the Earth is now moving to the left, the light will shift northward. And that's what he really detected. He detected that southward shift and that northward shift, and by looking at the star. So let me stop there for a second. That's the review. Any questions on any of that or comments? Anything in the chat I don't see yet? Okay. All right. So let's move on now and let's look at this explanation in the light of the corpuscular theory a little more clearly. And to do that, I'm going to give you in the next few slides hopefully a a really nice look at what's called Galilean relativity. Because what I want you to come away with from this time is to appreciate that the motion of the Earth is completely irrelevant here, other than the fact that the Earth is looking at the star in different reference frames. When the Earth changes its motion, it's now in a different reference frame, or it presents a different reference frame to look at things. But in Galilean and Newtonian physics, there was no absolute rest frame. Every frame had perfect right to consider itself to be not moving. And I want to convince you that what Bradley saw, and Bradley would agree with this, Newton would agree with this as well, is that all these observers are doing is looking at a star where it is. There's no motion involved in aberration. There's just looking at a star where it really is. The light comes from the place it was emitted and comes directly to you without any motion of it or you being involved. You can be moving, and that might change with time where it appears. It can be moving, and that might change with time where it appears. But the light that you observe it with is simply light that came straight to you from where the star was when that light was emitted. And it comes to you at an angle determined by nothing more than that. Your motion is completely uninvolved. Having said that, I'm gonna refer to the motion all the time, so there'll be a little. I'll have to explain that a little bit. So here we are, a simplified version. I've made the speed of light here 12 miles per hour, just so we can see bigger angles going on. But the same principles will apply when we let it speed up by, a few orders of magnitude. So here's a star. I've just got this. I'm showing this view from the reference frame of the blue guy, the guy in the middle. Because you notice he's, quote, not moving. Well, it's not that he's not moving. All I'm really saying is we're looking at it from his reference frame. And he has just as much right as anybody else does to consider himself to be not moving. So this is a picture of the way things are at the instant that the light is emitted from the star that he will eventually see, the light that we will be interested in him looking at. So the star is up there. It's 12 miles away. It's moving to the left at 3 miles per hour. And meanwhile, there's a green guy 5 miles away moving toward him at 5 miles per hour. And there's a red guy 9 miles away moving toward him at 9 miles per hour, while the light that they're going to look at, the light we're going to be interested in, is being emitted from the star where it is at that instant, 12 miles away from the blue guy and moving at 12 miles per hour. So I hope you can all see what's going to happen an hour from now. If there's any questions on what's going to happen an hour from now, you can ask. But let's see. Let me just look at it. I just want to be clear about a couple things. The star is emitting light in all directions. It was emitting light before it got to that position. It'll emit light after it got to that position. But the only light we're interested in are the light particles that are emitted at this instant of time and that are moving toward the blue guy in this picture. That's the light I'm interested in. Okay, so are we good on that? We'll move on to the next slide. So slide 6, I'm showing that again. I'm showing you the initial situation again, but I'm also showing you what things look like from the same reference frame, the reference frame of the blue guy, 1 hour later. 1 hour later, everybody is in the same place, and the light is also at that place. Still moving at 12 miles per hour. Maybe it's going to be seen. Maybe it'll be absorbed by the retina of one of their eyes. But there'll be plenty of particles around it that might not be. So there'll be some light that continues on. We can consider a bunch of little particles headed toward, some of which go into the retina of the blue guy, some go into the green guy's retina, some go into the red guy's retina, etc. And of course, the blue guy sees the star right up there, right up above him, but the star's not there. That's not where the star is. That's only where the star was. when it emitted the light. The star is now 3 miles to the right. And if the blue guy knew something about its velocity, because maybe he'd been watching it for a while, he could probably predict that that's where it is. But he's under no illusion that he should be able to see it there, because the light from that position hasn't gotten to him yet. It'll take another hour, a little more than an hour, for that light to get to him. Okay, so they're all right there. They're still moving with their velocities. The light's still moving, but the light comes into the retina of the blue guy, and he now sees that 1 hour ago. And he doesn't. And by the way, he doesn't know that it was an hour ago. All he really knows, he doesn't really know how fast the star is going or anything else. But what he knows for sure is that when the light that he's now seeing from that star was emitted, the star was directly overhead. That's what he knows. Okay? And because it's really important to be clear about what we know. And all he knows is that he's seeing a star directly overhead, and therefore, at the moment that light was emitted, at that moment, the star was directly overhead. Okay, so let's move on to, actually, first of all, let me just take a look. Okay, yeah. So slide 7. So what we're going to do now is what's called a Galilean transformation to the reference frame of the green guy. I want to see what all of this looks like from the green guy's point of view. And to do that, I'm simply going to go into what's called his rest frame. That implies a Galilean transformation, whereby I simply take everything where it is. I might use a different coordinate system. I haven't actually put a coordinate system into any of this because I don't really need it. But what we're going to do is simply say, well, to go into his rest frame, I need to move with him at 5 miles per hour to the right. That's going to make everything else look like it's moving to the left at 5 miles per hour, or I should say more to the left at 5 miles per hour. Whatever its current velocity is, I'm going to just have to add that 5 miles per hour to it. So when I do that Galilean transformation, you see over there on the right, now the green guy's at rest. The blue guy is now moving at 5 miles per hour toward him. The red guy's moving at 14 miles per hour toward him. I've added 5 miles per hour to both of their velocities. And when I add the 5 miles per hour to the light's velocity, I have to do what's called a vector addition, because those two velocities aren't collinear. The 12 miles per hour is downward, say, in this diagram, and the 5 miles per hour is to the left. And when I add those two velocities, doing a vector velocity means just making that little triangle and seeing the net result of both moving down and moving to the left. 12 down, 5 to the right. If you do the Pythagorean theorem, I chose those numbers for a reason, because 5 squared plus 12 squared is 13 squared. So the light from the green guy's point of view is moving at 13 miles per hour. And maybe if you do the same Pythagorean theorem on the distances there, the 5 miles to the blue guy, the 12 miles to the star, you'll see that the distance that light is going to have to travel to get to the green guy is also 13 miles. So the green guy, when that light gets to him, that light, it's the same light. I just Galilean transformed its velocity. It is the same particles of light are now moving at that 22.6 degree angle, and they're moving directly toward the green guy, and they're going to get to him in an hour. All right, so now on slide 8, let's take a look at that. There's once again a reproduction of the transformed view, the view from the frame of the green guy. Now what happens? The light gets to him in an hour, so an hour later, what do we have? The blue guy has gotten to him, has come to him. The red guy has come to him. They've both gotten there because it's 14 miles to the red guy. 14 miles per hour gets him to the green guy too. So once again, they're all right there at the same time that the light gets to them. But in this case, since we're looking at it from the green guy's point of view, the green guy sees the light coming from that direction and says, Ah, there was a star up there in the direction that that black arrow is pointing with the question mark on it. There's where the star was when it emitted the light. And indeed, that's where it was when it emitted the light. But now, of course, the star is 8 miles to the left of that because it's now moving at 8 miles per hour in his reference frame. And if you do a little calculation, you'll see that means 3 miles to the right, to the left of overhead for all three observers. They all agree that right now the star is 3 miles to the left of directly overhead. So it's interesting to see that, they all see different things, but they understand why they see different things, and they understand that they're all seeing the same thing, it just looks differently because of their different reference frames. So let me stop there for a second. Again, we're going to do one more Galilean transformation, then we'll be done with that. Everybody with me? All right, so let's do the last one. Let's just do it from the red guy's point of view. Maybe look at 8 and notice that if I'm going to go into the reference frame of the red guy, I'm going to have to take all of these velocities and add 14 miles per hour to the right in order so that the green guy now will look like he's moving toward the red guy at 14 miles per hour. The blue guy is going to be moving toward at 9 miles per hour, etc. If you go to slide 9, you'll see that. So doing the same kind of a Galilean transformation now, from the reference frame of the red guy, the star is moving 6 miles per hour to the right now, not to the left. The green guy's moving 14 miles per hour, has to travel 14 miles to get to the red guy. The blue guy is traveling at 9 miles per hour and has to travel 9 miles to get to the red guy. The star is 9 miles to the left and 12 miles high, according to the red guy. 12 squared plus 9 squared is 15 squared. I chose those numbers for a good reason, too. And so the star is 15 miles away from the red guy. And if I add the 9 miles per hour, 9 miles per hour to the left to the 12 miles per hour down, as I've shown in that vector diagram over there to the left, I get that the light is traveling at 15 miles per hour directly toward the red guy. So in the red guy's frame, that same light, the same light that was traveling directly toward the blue guy in his reference frame, is in this reference frame traveling toward the red guy. It's the same light. And in the red guy's reference frame, it is not traveling toward the blue guy. The blue guy completely understands why the red guy thinks that, because he can do the Galilean transformation, right? Not just thinks that, but sees that. The blue guy knows that if he were the red guy, that's exactly what he would see. So there's no mysteries here. And when the light gets there, when they all get there, when they all get to the red guy, the light, the blue guy, and the green guy all get to the red guy, 1 hour later, the red guy is now seeing that light and seeing the star where it was when it emitted that light. So all of these look like very different ways of seeing things. They all disagree on where the star is, but every one of them is just seeing the star where it was when it emitted the light, and that light came directly toward them, and they are not moving. It's just light that comes directly toward them, and there's no need to invoke motion whatsoever to understand that. And yet it does look a lot like moving through rain in different directions. So we'll come back to that in a moment, too. So I'm done with the Galilean transformation business. Any comments or questions on that?
So I just want to be sure about this. So an hour into this thought experiment, the RGB guys are all in the same spot, and they all agree that the light they see is straight up.
No,
They,
only the blue guy agrees that only the blue guy sees the star straight up and understands that that's because the star was directly overhead when it emitted that light. The green guy, for instance, you can see in the first diagram for the green guy that the star is over there in kind of to the left, or to the right of him and high, right? And that's where he sees it, right? The blue guy understands that the green guy doesn't, that the light that the green guy is going to see didn't come from a place that was directly over his head because the green guy was 5 miles to the left of the green guy, of the blue guy. The green guy was 5 miles to the left of the blue guy when the light was emitted from that star that the blue guy is going to see and the green guy is going to see. The green guy is going to see that same light and it's going to have come from the same star at the same time when that star literally was 5 miles per hour to the right of the green guy. There's no there's no mystery in the fact that the green guy sees it to the right. But it is weird. I mean, I'm not trying to say it isn't weird, but that is a really important thing to understand is that every one of them, in a way, I wish I hadn't put the star directly over the blue guy. I shouldn't have been directly over any of them. They would all see it exactly where it was when the light was emitted, and all of them would understand that they're seeing it where it was. It's just that they disagree on kind of that question of where was it. Green guy says, "Oh, it's to the right." The blue guy says, "No, it wasn't. It was right overhead." The red guy says, "No, it wasn't. It was to the left." But they all see that. It's because they were to the right and left. Okay, maybe I belabored that point. Did that help at all?
I think I'm thinking about this wrong, but I'll keep thinking about it.
Well, I would like to, if there's any way to phrase the question maybe again or ask it again,
Well,
maybe I will dig
I
out a
see
little
how
more what you're
initially
confused about.
they're looking different directions.
Well, they're
But
not
my thought,
looking. Remember
my
that. Oh, let me. This might help. This might help, Andy.
okay.
At the moment that I show in that first diagram, they're probably all seeing the star, right? But the blue guy is going to see it a little to the right because that's where it was when it emitted the light that the blue guy is now seeing. I'm not talking about that light. If the blue guy were to look at the star right now, not an hour later, but at the beginning, the blue guy would see it somewhere off to the right because that light getting to him now came from the star earlier. And so would the green guy, and so would the red guy.
This reminds me of skeet shooting,
Yeah,
if anybody's ever done that.
you have to lead, right?
Yes, maybe from a moving car.
Yeah. No, I think I think maybe that might have been part of the question. It's not a question of what where they're looking now. It's a question of where they'll see it at the hour later thing. If you do a detailed look at what they're seeing now, it's complicated because the light that the blue guy is seeing now came from the star when it was a little more than 12 miles away. So it was a little more than an hour ago, right? Same thing you could say for the green guy. It came from the star when it was further away, and so it was a little more than an hour ago. But for the red guy, the light that the red guy is seeing now actually came from the star less than an hour ago, because for him, it has to travel less than that 15 miles since the time that it was, since when it came, when it was emitted from the star, it was closer to him than it is now. These are all kind of, yeah, you really have to think carefully. It's funny how this is all the stuff I'm talking about now actually is the perfectly intuitive universe that Newton described. And yet it's strange how our intuitions get bollocksed up when we actually try to do something as fundamentally simple and kind of obvious, really, as a Galilean transformation. If you think about what's
So
going on
here's
in the
where
Galilean
I've ended
transformation.
up
Yeah, go ahead.
with my thoughts on this. If the star is moving, then the observer will perceive the star where it isn't at the moment. If we assume some kind of universal time, which we can't do. But
Mm-hmm.
um, if if the observer is moving, it doesn't really matter because um, the light is just there where it would be. And if you move into it, you may shift its frequency a bit, but you're still going to see it. as you move into it.
But
Now,
just remember that particles
if
don't have frequencies.
if you, I didn't say that they did, right? I said that the frequency would shift if the observer was running
Yeah, I
into the
really
light.
don't want to bollocks this up with Doppler ideas. That'll come. One of the things I'm really trying to do is put us in the heads of people who lived in the early 1700s. And these people had particles, right? There's no Doppler shifting going on. That's that's something
So
waves do.
if you move, you'll see the light at the same as if you didn't move, but the way you observe it into your eye, I guess it would move. It would appear to be more in a straight line. If you move infinitely fast, it would look like all the light is coming sort of at you and none of the light is coming from behind you. So the faster you move, the more the appearance of the world is sucked into a cone
Yeah.
in front of the
So let me
motion.
say a
Is that
couple
right?
things about that. First of all, every time you say something like if you move, you're kind of implying that you can move, that there's a meaning to saying you're moving, that there's a meaning to saying the star is moving. There's no meaning to that. When you say something's moving, all you're saying is that you see it moving or something sees it moving, and you can specify how
Okay, but
fast
time
it's
out
moving
because
to that thing.
I'm gonna pull a
Yes.
Machian move on
And that's going to come up here
you
too. That's right.
and
So,
say
so let me,
that
for instance, so
while
before you
you're
do, just before you do, let me point out that in this world you can move faster than light. And so, if I move fast enough, the light from something will never get to me. I will not be able to see it if I'm moving faster than the light from it. So, go ahead.
well, that's why I kind of assumed that as you go faster and faster, all observances shift to coming in
Right,
front of you.
right. And that
Um,
happens in relativity
the,
too, interestingly enough. So go ahead.
but the Machian move here is to say that while absolute motion is a fiction, uh, orbital motion is a fact. And if I understand it right, it's very important here that this is the Earth is in an orbit around the sun, and that is a Machian rotational frame, which means it's an absolute frame.
Yeah, so I don't want to.
And
I don't want to move too far ahead. Mach will come up about 150 years from now, so
well, so
we'll get to
all I
that.
would say about this is that because you have the going forward speed of one side of the rotation, the going back speed of the other side of the rotation, you can at least compare those two speeds,
Right,
and that is meaningful in a
right.
way
So
that saying
so I
something's
think
moving is not.
another way of saying what you're saying now, and something I haven't pointed to yet, but want to just as we're leaving, is that notice there is one difference between. There's one genuine difference between these three people. What is that? I think you're kind of hinting at it. There's one difference in the universe, in the laws of physics, if you want to think of it that way, for these three people.
Yeah, I'm not going to pick that out. I don't think somebody else maybe take a shot.
What do you see? So, for instance, what is one thing we haven't talked about here is quote the speed of light. What is the speed of light in the universe that we're talking about here?
I mean, I saw 12 miles an hour. Isn't that?
Well, see, and that's the danger of me having shown that reference frame first. That's just one of three completely equivalent reference frames. There's no reason to think that what the blue guy says is any more important than what the green guy says or the red guy says. So, what is the speed
Well,
of light?
the blue guy is a little bit different in that he has a coaxial frame with the light, if I understand this correctly.
Well, okay,
And the
fair
other two
enough,
have a
and
complex
that's
relationship.
but that is why I shouldn't have. I really should have let the star not be overhead any of them. I could have done this same example and had the star just at some place between the blue and the red guy. It wouldn't change any of the points I'm trying to make here. I just had it overhead because that made two really nice triangles, a 5, 12, 13 triangle and a 9, 12, 15 triangle, which I kind of liked. So that's why I did that. But there's nothing special about it. The blue guy says, oh, that light's traveling at 12 miles per hour. The green guy says, no, it's not. It's traveling at 13 miles per hour. And the red guy says, no, it's not. It's traveling at 15 miles per hour. And none of them have any trouble with that because light is particles. And particles can travel at any speed they want, right? There's no, what do you mean the speed of light? That's ridiculous, right? Light is just particles. If I move at 100 miles per hour and that particle's at rest, then I'm going to say that particle's moving at 100 miles per hour. It's that simple. So and the real point I want to make here is there's some really deep physical questions in this story about what light is. Light does seem to be really fast. Why is it that we don't ever see light traveling at 1 mile per hour? If it's particles, why don't we ever see it just traveling at 1 mile per hour? Right? All we have to do is travel as fast as it, and it will be. So there are some real questions there. One more comment, maybe, and we'll move on because I do want to say a few more things about that. So let's do because we're kind of getting into the questions of slide 10 when we do this. So we have three observers, each with equally defensible or equally indefensible, if you like, claims to be at rest. Each one sees a different velocity of light, different in both direction and magnitude. And it's just from this one star, right? If they were looking at different stars, they'd all see different velocities, depending, right? If there was a star, if they were looking at a star that happened to be directly over the red guy's head at the initial time, they'd all get different results for that one as well. So what could we even mean when we talk about the speed of light? Light obviously can't have a speed. There's at least, at the very minimum, there has to be a wide range of possible speeds. Kind of that range would correspond maybe to whatever the range of possible speeds I can have is. If there's some limit on my speed, then maybe there's a limit on the speed of light. But I don't know of any reason why I couldn't go at any speed I wanted. So it seems like light could travel at any speed. But then again, is there really any reason to be concerned by it not having a definite value? By it depending on the motions of the source and the observer? If it's a particle, it's just going to have to be that way, and that's the way it. And they figured that's what they thought at the time. Maybe those different possible speeds are associated with color. Maybe faster particles are violet and slower particles are red. In fact, there was probably good reason to think it was just the other way around. Red light gets refracted less by a prism. Maybe that's because it's traveling faster and it doesn't get bent as much or something. So maybe it's associated with colors. Strangely, there doesn't seem to be much indication that they played with that, other than the fact that some people looked at it and said, maybe light particles actually do travel at all speeds, and only those in a certain range of velocities are sensible to the human eye. Maybe there's light traveling at all different speeds, but only those traveling kind of, close to 186,000 miles per second. They didn't know that at the time. But maybe those only in a small range of velocities are the ones that are seen by the eye. And maybe, once again, they're associated with colors. Maybe when we move toward a star, some of those light particles now are moving at a speed that we can't see, but ones that we couldn't see before we do see, because now they're traveling at the speeds that we do see. That kind of stuff was really thought about. We're going to see next time that Arago thought about this in terms of refraction, thinking that when we move toward or away from a star, it should be refracted differently because the speed of these particles would be different. And so we should see some refraction difference. If we put a prism in the way of starlight, it should shift those stars, that light more or less depending on how fast the star is moving. And Newton had shown that there are invisible effects outside the visible spectrum. He took white light, spread it into a spectrum, And then he showed that on near the red end of the spectrum, he could make things heat up just by putting them there, as if some rays were hitting them that he couldn't see. He really literally discovered infrared light by showing that there was something going on to the side of the on the side of the red side of the spectrum that we couldn't see. And he did the same thing on the violet side. He showed that he could make little chemical reactions happen with whatever it was that was going on the violet side. That's a fascinating thing to me. He actually thought maybe there are rays that we can't see on either side. Let's see if I can see any effects. And then he thought to see if those rays would heat things up, if they would stimulate chemical reactions. What an amazing thing to think. And they did. So he actually discovered both ultraviolet light and infrared light by doing those things. So that's kind of the place we are with this corpuscular theory. Any comments or questions on that? Or really, the thing I'm really trying to do is put you in their heads. I want you to forget about anything you think you know about light and just think about this, what you would be thinking if you had these Bradley observations, this idea of Galilean relativity, and and the things we know about light and prisms, etc. Okay. Now, I see in the comment Jeremy saying that you put light through a medium to slow it down, and that's true, but they didn't know that. They didn't know what was going on in a prism. That will, by the time of next week, we will know that that's the kind of wave, that's the Fresnel-Huygens understanding of what's going on in refraction is the slowing of light. So we will get there. And I think, and certainly Newton and others thought that slowing and or forces making things change might have something to do with what's going on in a medium, that maybe it travels more slowly too. But they didn't have Snell's law. They had no mathematics to back up how much these rays should bend or why they should bend as they do. But yeah, all of that we're kind of getting to as well. Okay, all good with slide 10. So let's move back now. Having told you that I don't want you to think of it as rain, let me move back to the rain idea, and look at the same thing we're talking about, but I'm going to draw slightly different diagrams. This aberration purely in the context of light direction, not the place it's coming from, but just the direction it's going. So I want you to think now about this same star that we were talking about before, but let it be enormously far away so that even large lateral velocities won't change its directional position very fast. So if I take that same star and I put it very far away, remember I said the blue guy would watch the star and he would see it moving across the sky pretty quickly. The image of it would be moving at about 3 miles. The thing he saw, that light in the sky, would be moving to the right at many degrees per hour because the star is moving at 3 miles per hour, and in an hour it would be 3 miles to the right, which would be some pretty good number of degrees. That's about 20 degrees or something. So a degree every few minutes it would be moving along. But if that same star were really far away, then the light that he would be seeing right now would have come from that star an enormously long time ago. And it wouldn't matter if it was 3 miles to the right or left. It would still be coming from so far away that it would be looking like it's coming straight down. And to make that a little clearer, in reality, stars, the closest stars are about 100 trillion kilometers away, 10 to the 14th kilometers away. That's a very nearby star. There are a few stars closer than that, but not very many. And if that star were moving at 100 kilometers per second, that's a pretty typical, maybe on the high end, but a pretty typical relative speed for nearby stars. if it were moving at that speed perpendicular to our line of sight, so that it would be, apparently moving quickly, angularly, changing its apparent direction, then in that case it would be changing its apparent direction by 100, the 100 kilometers per second, divided by the 100 trillion, the 100 trillion kilometers. 100 divided by 10 to the 14th radians per second, you can convert that to arc seconds per year. That's 6 arc seconds per year. So a star that was doing that, and there are stars that do something like that, would be changing its position in the sky by 1/10 of 1/60th of 1 degree per year. That's 6 arc seconds per year. And that kind of motion is called proper motion. And we see that kind of proper motion. Nearby stars do change their position in the sky by numbers of arc seconds per year. So that really does happen. But to a casual observer, you won't see that kind of change in less than 1,000 years. It'll take 1,000 years for that to mount up to something where a constellation now begins to maybe look a little bit different than it did 1,000 years previously. Okay, so this rain thing is very appealing. That's what I'm trying to say. It's really tempting to view aberration using motion through rain analogy. All three of those observers are going to have this rain coming down at that 12 miles per hour that the blue guy sees. And then when the green guy moves at 5 miles per hour through that rain, he's going to have to look a little bit, not straight overhead, but he's going to have to look a little bit to the right in order to see that star. And I want to emphasize that nothing has really changed. The light from that star left so long ago, especially because it's only moving at 12 miles per hour, that it was over there. It's enormously far away, but when that light left, the star was enormously to the right. So nothing changes about it, but it's just much easier to think about it as moving through the rain. If you move through that rain, that's what you're going to see. And so on slide 12, I just show that. We do the Galilean transformation, and we get the same results we did before, as if it were just a rain of particles coming down. The green guy sees 13 miles per hour at the 22-degree angle. The red guy sees 15 miles per hour. I didn't say it before, but it's about a 37-degree angle the other direction. So they all see the same thing. The rain analogy is very tempting, and it works. It gives the right answer. But I just want to emphasize over and over again that each one of these guys is seeing the star where it was when the light left. And everyone has the perfect right to consider themselves to just be sitting there waiting for the light to get to them. Ben? Oh, I see you unmuted again. Sorry, maybe that's just me, not PT. Yeah, I think you're unmuted. I do not. Is it just me again?
I think it's a bug.
Maybe so. Okay, now I see you as muted. That's weird. Okay. All right. So any questions, comments on that? The rain thing does work, gives you perfectly good example, but it has this unfortunate side effect of making you think that that aberration requires motion, requires the observer to be moving, and it doesn't. All each observer is doing is seeing the star where it was in their rest frame when that light left. All right. So anyway, with that in mind, and we'll come back to that. So that's just an important thing to keep in mind, because when we move to the wave theory of the 1900s, of the 1800s, the 19th century, we're going to see that now that's not what people see. Only people that are in the rest frame of the medium that the light has to have in order to be a wave see the object where it was when that light was emitted. Other people are going to see it in a different place because that light is going to be carried with the medium, or if you want, you're moving through the medium. So you're no longer seeing it where it was when it left. But that's a feature of the wave theory. I emphasize that in the wave theory, it's not the case that you see the object where it was when the light was emitted. Okay, so let's just talk then. I have just a few more things here about the details of stellar aberration, just so we're really clear about what it looks like. So modern measurements of stellar aberration are much more precise than Bradley's, hundreds of times, thousands of times more accurate than Bradley's. But they are in complete agreement. And yeah, he had higher uncertainty, but he got the same thing. And his explanation for it is largely proper. It turns out if light was traveling at a lower speed, his explanation actually wouldn't have worked because relativity gives a different answer. But the difference that relativity makes no difference in the measurements. You get there's no detectable difference in aberration between the relativistic explanation and Bradley's explanation. They're both identical at the level of even modern measurements. So once again, unlike parallax, which is noticeable only for relatively nearby stars, aberration affects every star in any given region of the sky identically. If a star shifts 10 seconds to the east or something, every star near that star shifts 10 seconds to the east. And the best way to understand that, once again, is thinking about the rain analogy, right? That rain from that region of the sky coming down, you moving through it, if you want to think of it that way, and thereby every star shifts by the same amount. But it changes over the course of a year because the velocity that you're moving, being carried by the Earth, is changing over the course of a year. So, as I said that already. So so in the case of both parallax and aberration, the apparent motion of the star is an ellipse. And in both cases, the ellipse has a semi-major axis that is parallel to the ecliptic plane. So no matter where the star is in the sky, it suffers the same aberration to one direction or the other in the direction that's parallel to the ecliptic plane. In other words, the direction that's parallel to the direction that the Earth actually moves. For every star in the sky, there are 2 times a year where the motion of the Earth is perpendicular to the line of sight. If you think of that's a little geometry problem for you. Think about the Earth moving around a circle. Pick any point in space and see that there'll be 2 places on that circle where a tangent is perpendicular to the direction to the star. And those 2 places are diametrically opposite. So at one of those places, you'll see the star maximally shifted in one direction, and in the other place, you'll see it maximally shifted in the other direction, and those directions are in the same direction as the ecliptic plane, which is why you get that. For stars that are directly at what's called the ecliptic pole, this is an interesting concept too. Stars that are directly perpendicular to the plane of orbit of the Earth. That's not Polaris. Polaris is perpendicular to the equatorial plane of the Earth, but the equatorial plane of the Earth is tilted at 23 degrees to the ecliptic plane, the path that it takes as it revolves around the sun. Turns out that stars in the constellation Draco are basically directly overhead or directly perpendicular to the ecliptic plane. So stars in the constellation Draco execute nearly perfect circles of this with what's called the aberration constant as their radius. That's 20 point, we now know it to be 20.4995 seconds of arc. 20.5 arc seconds will be good enough. So those stars go around, stars at 90 degrees to the ecliptic go around that black circle. South of the ecliptic, the stars at the southern ecliptic pole execute counterclockwise motion around that circle, and stars at the northern ecliptic pole execute clockwise direction around that circle. And as you get closer to the ecliptic, at 60 degrees, it gets a little squashed in the direction perpendicular to the ecliptic, 30 degrees squashed a little more. And stars that are in the ecliptic plane just move back and forth. And you should be able to kind of understand that if you think about this plane of motion of the Earth, then there are 2 times a year when the Earth is moving perpendicular to the line of sight to that star. But at the intervals that are perpendicular to that, 3-month intervals if you want, there'll be a time when the Earth is moving directly toward the star, and a time when the Earth is moving directly away from the star. There's no shift when the Earth moves directly toward the star, and no shift when it moves directly away. There's only a Doppler shift, as Benjamin was saying earlier, but that's 150 years in the future from where we're talking about right now. So Bradley figured all of this stuff out, and it's exactly what we see for all the stars in the sky. And let's see. And I have actually maybe the best. I probably should have gone to slide 15 first. Well, yeah. Actually, let's just go to 15. I don't know why I didn't do that first. 15 kind of shows how this works. I took a snapshot from Stellarium of what the sky looks like from Los Angeles, where I am, at 8:15 in the evening last night. So 8:15 last night, this is what the sky looked like. Draco was right down there, just south of Polaris. The ecliptic plane, the path of the sun through the celestial sphere, was intersecting at my where I am, due west and due east, and then kind of arcing overhead like that. This is a kind of a serious fisheye lens view of the sky, I should point out as well. And I've drawn little circles and ellipses there showing the aberration paths of stars in different parts of the sky, and the direction that that aberration shift will move around during the course of the year. You'll see there's a couple of them that are on the south side of the ecliptic. They're moving counterclockwise, while all of the paths within the ecliptic are moving in the clockwise direction, because those are all north of the ecliptic. I don't see many stars. To see stars south of the ecliptic, I have to look to the south, and I'm looking to the north in this picture. And I'm also showing the current shift due to the fact that right now the Earth is moving toward Libra. So all of these things are shifted in the direction toward Libra as well. And I should also point out, I have never seen a picture anything like this, and I might have made a mistake or two in drawing it. I put this together just to satisfy my own curiosity, because I could not find this diagram anywhere on the web. So if anybody does, please let me know, and especially let me know if I've made some kind of a mistake. I think it's kind of fascinating. I'm surprised that it is so hard to find, but maybe that's just an indication of my level of geekiness. I'm not sure. So that's slide 15. We're going to go back to slide 14. Let me stop a second. I've been talking a mile a minute here, I know. Okay, hearing no takers, we'll finish this up and just open it up for general. Let's go back to slide 14. I have talked in the past, in fact, I did last week, about the value that Bradley got for the speed of light. I had an interesting conversation with Google Gemini last night, trying to understand this better, because I happen to know that at the time of Bradley, the distance to the sun wasn't known that accurately. There were a couple of estimates that weren't very well done. One was based on an assumption that turned out to be pretty good, but wasn't very good. But the one by Huygens, he determined the distance by assuming that Venus is the same size as the Earth, which isn't a bad assumption, but it's not right. And then there was one other assumption, one other measurement using the parallax of Mars. But we really didn't know the distance to the Earth, and yet people talk about distance to the Sun, and yet people talk about Bradley getting a value for the speed of light, which would have required him to know how fast the Earth moves, since the aberration angle is just the ratio of the Earth's speed to the speed of light. He didn't, it turns out, Gemini was trying to tell me that he did determine a speed of light and was trying to tell me that he did it using the astronomical unit, distance to the sun, etc. A couple times I pointed out that to Gemini that it was making a circular argument that required it to know one thing in order to calculate that same thing. And of course, it was very polite. It agreed with me, as it always does. Of course, whenever you point out it's made a mistake, even if it hasn't, it always agrees with me. But in this case, it had. I went through about 3 or 4 things. And then finally, we both agreed together. I said, could it be that what he really used was something just about the ratio of the speeds without actual, or the I can't remember what I said, but anyway, we finally got to this. And it turns out it's pretty simple. He didn't know how far it was to the sun, but he did know that the velocity of the Earth, whatever that is, and he didn't know that either, is it's the circumference of its path divided by 1 year. Whatever that is, he didn't know that either, divided by 1 year. That he knew. He knew that the Earth goes around its path once a year. And since the distance to the sun is related to the time that it takes light to travel from the sun to the Earth by the speed of light equals that distance divided by that time. That's just V equals distance over time again. He knew that, and since his aberration constant, which he had as 20.2 arc seconds, which is 0.0000979 radians, he knew that that angle was just the ratio of V to C. So it's simple algebra from those equations to show that the time it takes light to get to the Earth from the sun is just the aberration constant times 1 year divided by 2 pi. Well, 1 year divided by 2 pi is 5,023,000 seconds. And if you just multiply that by the aberration constant, 0.0000979, you get 492 seconds, which is 8 minutes, 12 seconds. And you can compare that with the now known range from like 8 minutes, 20 seconds to 8 minutes, 27 seconds between perihelion and aphelion. That's how long it takes. His time of travel number, which is kind of equivalent in some sense to the speed of light, even though he didn't know the speed of light, didn't know the speed of the Earth. He did know the time it takes light to travel from the sun to the Earth to an accuracy that was not surpassed for nearly 200 years. Bradley's kind of effective value for the speed of light wasn't bettered until the beginning of the 20th century, which I think is really another truly amazing kind of historical fact. All right, so we'll finish finish up here, just looking forward. Looking forward, as we will see, this 18th century corpuscular theory of light was replaced. We're going to kind of jump 100 years ahead right away next week, because almost nothing really happened. Nothing really important happened with the corpuscular theory, except that people started thinking about the wave theory. It got better and better accepted until at the beginning of the 19th century, it did replace the corpuscular theory. It was impossible to deal with diffraction and refraction and interference effects of all kinds with anything but Huygens theory, as supplemented by some serious mathematics from Fresnel. So it'll be replaced by this wave model, and the cost of that now is that we now have to have a wave. All physicists understood that there had to be a medium. We now talk kind of in a historically revisionist way about what physicists having this big battle about whether or not there was an ether. There was no battle about whether the ether existed. It had to exist. The only question was, how fast do we move through the ether? How fast does the Earth move through the ether? That was the only question, not whether the ether exists. It had to, because all waves have to have a medium. That was well understood. And so that is the mindset that will be in next week. This new wave model establishes now a preferred reference frame for light. There are people who are at rest with respect to that reference frame, and those people have a preferred view of things because they see things where they were when the light was emitted. The thing can be moving, but they can't. The thing can be moving through the ether, and all we will see if we're not is where that thing was when that light was emitted. But we're the only people that will be able to say that, because if you move relative to the ether, you will see things in a different place. You're moving now. You really are moving now. And so your view is different from the view of the person in the preferred reference frame. Okay. And in fact, with good enough measurements, you can now there is, by the way, now there really is a speed of light, because the speed of light, the nice thing about the wave model is that it makes sense to talk about a speed of light, because the speed of light is determined by the stiffness and inertia of the ether itself, just like water waves are determined by a kind of a stiffness and inertia of the waves conferred by gravity and the mass of the water, etc. Waves on a string are conferred by the tension in the string and the mass per unit length of the string. Sound waves are determined by the elasticity of air and the mass of the air. All those speeds are always determined by properties of the medium. So now it makes sense to talk about the speed of light. And if you measure the speed of light in three mutually perpendicular directions, you can then figure out how fast you must be moving relative to the medium that light is traveling through. So all of that, and that's, of course, sets the frame for all of the things that we're doing in order to determine just that. How fast are we moving through that medium? But we will also see, maybe not next week, but the week after, that repeated and increasingly accurate failures to detect any difference in the speed of light, no matter, now and 6 months from now, no matter what we did, led to the theory of relativity, which actually eliminated ether in favor of a completely bizarre hypothesis that simply says, okay, everybody observes the same speed of light in all directions, regardless of how fast the object that emits it's going, regardless of your own motion. The speed of light in a vacuum is the same for all observers. That is a ridiculous hypothesis, and it predicts ridiculous things, all of which have been confirmed experimentally to happen. So that's kind of where we're going. And I should mention, a lot of times you'll hear people take issue with whether Michelson and Morley actually showed that there was no difference. Well, okay, you can say that, but modern versions of the Michelson and Morley experiment have failed to detect any motion of the Earth through the ether down to now a level of 1/10 of a millimeter per second. If the Earth is moving through the ether, it's not doing so any faster than 1/10 of a millimeter per second. So that's kind of where we are now. Anyway, we'll get there probably 3 weeks from now, maybe 2 weeks from now. Okay, I'm done. Thanks for your patience, everybody. I hope that was a fun story, and I hope you all can If there are questions still about things, I really, really would like to take them and try to maybe say better what I've tried to say in this episode. This episode I think is has lots of really important stuff in it. So sleep on it or ask questions. Thanks. I'm done. All right. So, and we can look ahead a little. I know you're probably itching to look ahead a little bit. We can do that as well.
Me?
Or we can say goodnight
I
and
mean,
go
the tricky
kiss our
thing
kiss
here
our
is that
lovers. It is Valentine's Day. Go ahead.
there's no controversy.
No, there's no controversy yet. You mean? Is that what you're saying?
Yeah, I mean that's why there's no conversation.
Yeah. Well, I see some controversy in the chat. I guess somebody who doesn't think maybe that there actually is aberration. I can assure you that there is aberration. So there's always it's kind of we get into questions like this thing. You'll hear flat earthers say things like, "Well, I don't believe in gravity," or and usually because it's religiously motivated. Flat earthism is typically religiously motivated. There's usually also, "Well, I don't believe in evolution." And you don't have to believe in them. Those are directly observed facts, right? Gravity is a name we give to a phenomenon that's a directly observed fact. Evolution is a name we give to a phenomenon that's a directly observed fact. Now, I'm not talking about bones in rock. I'm talking about the fact that you can go into the lab and see evolution happen, and we have an explanation for that now that's very compelling in terms of DNA and all of that. So you can still take issue with that theory. You can still take issue with the theory of gravity. But when people say they don't believe in gravity or they don't believe in evolution, just say, well, we don't really care if you believe in it. Those are directly observed facts, as is, I might add, the shape of the earth.
You would add that spooky action at a distance is directly observed
Actually,
fact.
I wouldn't. That's a nice in the context of what I was just saying. That's probably a good thing. I wouldn't say that spooky action at a distance is a directly observed fact. I would say that the that we give a name called spooky action at a distance to experimentally observed things that are directly observed facts. And I think that's the difference between us because I think you don't accept the experimental facts that we call spooky action at a distance. The interpretation of those facts in quantum mechanics sounds spooky and maybe is spooky and gets the name spooky action at a distance. But the phenomenon itself really is beyond question at this point.
Hmm.
Well, all right. Should we? Maybe we should go. Spend some time with our wives and husbands. It is Valentine's Day, after all, and I did bring my wife a cup of coffee before getting up. Of course, I always do that, so there's nothing special. I'll have to go do something else for her. All right. Call it good. Maybe we'll play out with another Valentine's Day song or two. All right, thanks everybody. I hope this was valuable. I appreciate you hanging around, and we will continue the story next week.